Good morning, everyone, and thanks for the kind introduction. It's a pleasure to be here this morning at the 39th International Conference on Computer Design to talk a little bit about some of my experiences in computer design and some of my thoughts on where we are today and where we're headed going into the future. I've titled my talk as Computer Design Question Everything because I think that is a situation that we face. We should be thinking carefully about all the assumptions that go into the process of designing computers today to see if there are opportunities that we've bypassed in the past, often for good reasons, but perhaps reasons that don't hold today. It's a special occasion for me because, as it turns out, my very first conference paper that I ever published appeared at ICCD in 1993, so quite a while ago. This was work that I had done as part of a master's thesis implementing an instruction scheduler for a binary-to-binary compiler. I was kind of more of a software person back at that phase of my career, and I was very happy to get a chance to present my work at this conference. And now I'm very happy to be back almost 3 decades later to tell you about some of the things that I've done since then. I'm going to start this morning's presentation with a flashback to what CPUs looked like when I was an undergrad and even when I started grad school. This is a die photo, or rather a plot of the die for the MIPS R2000 processor. In the middle here, you'll see John Hennessy, who was one of the key leads on this project as it was spun out of Stanford University. This was a very interesting design. It was a very simple pipeline. As you can see, we can summarize the entire design in just one chart. And in fact, we can plot the whole design out in a size where the individual devices are visible to the naked eye on a single plotter. That is a far cry from where things stand today, but nevertheless an interesting place to start because that sort of puts a milestone or a pin into the beginning of my career in this. Since the design of the MIPS R2000 processor, architects have been trying to improve the performance of CPUs by trying to reduce the amount of time it takes to execute a program. We can describe this using something called the iron law as proposed by Doug Clark, which breaks the time per program into 3 interrelated terms: the number of instructions per program, which is defined both by the algorithm designer or programmer as well as the compiler designer, who can introduce new optimizations that reduce the number of instructions per program, the processor designer, who has to make a decision about how much parallelism to try to extract from the execution of the program at runtime, and also finally the chip designer, who will determine the cycle time of that particular chip. Now, the amount of parallelism that we can extract, that middle term, has been a subject of heated debate for many decades. This slide just shows some studies from the past that have indicated that, hey, maybe there's as much as degree 90 parallelism. This is a study from Nicolau and Fisher in the early 1980s, to much more conservative estimates ranging from 1.58 to something a little bit over 2 instructions per cycle. Now, there's one particular study here, Mike Johnson's study from 1991, that claims the number is about 2.5. And to those of us who were active in the processor design community in the 1990s, we're all probably familiar with Mike Johnson's very famous book, SUPERSCALAR Microprocessor Design. I think every CPU designer in the industry, as well as every grad student, had a copy of this book, and I know mine was heavily marked up. So what is it that a CPU that tries to extract instruction level parallelism has to do? Well, this slide should hopefully capture what needs to happen. So what's shown here is a snippet of assembly code with a bunch of instructions that read and write registers and load from memory and implement branches. The program's data dependencies can be captured using what's known as a data dependence graph, which is shown in the middle here. We can see, for example, that instruction 2, which is this branch instruction here, reads both register 18 and register 2, which are written by instructions 0 and 1 respectively, which places these ordering dependencies between instruction 0 and 2 and instruction 1 and 2. And the implication of that is that we can't execute instruction 2 until both 0 and 1 have executed. And the purpose of a high-IPC or high-ILP CPU is to try to make sure that instruction 2 will execute immediately in the very next cycle as soon as its dependencies have been resolved. So the CPU has to do a number of things. First of all, it has to fetch and decode these instructions in their binary form. It has to construct this data dependence graph and represent it in hardware structures inside the machine. it has to then have hardware that evaluates that data dependence graph, so that as soon as 0 and 1 have executed, for example, we want to make sure that instruction 2 will execute in the immediately following cycle. And then finally, once all of the instructions have finished execution, we have to make sure that we make changes to the program state in a reasonable and ordered fashion that matches the original program order. So that's really the 4 things that the CPU has to do its job. And this is a high-level block diagram of a typical high-IPC processor. At a high level, this matches pretty much any CPU that you're going to buy today, unless it's a very low-power design for some embedded application. So again, the fetching and decoding happens in the front end. We're typically trying to fetch anywhere from 3 to 6 or even 8 instructions every cycle. In the dispatch logic, we have to construct this data dependence graph and encode the dependencies into structures in the issue queues or reservation stations of the machine. And then in the back end, we have to have logic that now traverses those dependencies as aggressively as possible and make sure that instructions get sent to execution units just in time, so that once they arrive in the execution unit, their operands are available right before they get there. And then finally, the back end has completion and retirement logic that commits state changes to the register file of the instruction set architecture, and also make sure that writes get committed to memory properly and in the right order. All right, so to design one of these kinds of CPUs requires many years. This is a diagram that illustrates the experience of the Pentium Pro design team in the early 1990s. So they started in the year 1990, and then about 3.5 years later, finished this design. And if we start here from conceiving the product, defining the microarchitecture, which typically would, at least to a close approximation, determine the amount of parallelism that's being extracted, and developing the performance model, that took them about 1 year. Then about 9 months they took about 9 months to implement a behavioral model and a structural model, and then 1 3/4 years to do logic design, circuit design, layout, and then another final year once the chip had taped out to do silicon debug to make sure everything worked correctly. So this is kind of the way life worked in the 1990s when we were designing computers. All right, so popping back to the iron law, where do we see this going next, right? We have kind of been talking about improvements in the middle column here in the CPI and improvements in the cycle time on the right-hand side. I think we can pretty safely say that there's probably not going to be a lot of innovation in that first term. We've gone from complex instruction sets like Intel's x86 to the ARM instruction set and many other reduced instruction sets like PowerPC, to the most recent example of this, the RISC-V ISA. And to first order, there's not really a fundamental benefit to be had from modifying the instruction set architecture. And also compiler optimizations have kind of petered out. There's been continuing advances there, but they're not as significant as one might have hoped. Cycle time is fundamentally, again, being limited by constraints in the process. So really we're up against the power wall, as we'll talk about in a bit more detail. So we're not going to see improvements in frequency, and in fact we haven't been seeing improvements in frequency for quite a while. So really all we have left is this middle term. As computer architects, if we hope to continue to design CPUs that provide higher levels of performance going forward, this is really where the game is at. This is where we have to focus our energy and our attention. And unfortunately, the sort of bag of tricks that was there in the desktop CPU and server CPU market has all been used, right? We don't really have any remaining tricks there that we can easily just kind of grab and deploy and utilize. So what are we going to do? Where are we going to go from here? Well, if you kind of look at what's happened over the last 25 or so years, we had compound growth of about 35% per year for a long time. But about a decade ago, that really slowed down for CPUs, and we've really only been seeing about 5% per year compound growth in CPU performance since about 2010, which is indicative of the fact that, again, we don't really have a lot of new ideas. We don't really have a lot of breakthroughs. We don't really have even much research going on in this space trying to figure out what we could do to do better than this. And in fact, if you look at a block diagram of the Pentium Pro design from 1995, shown on the left here, and the Intel Skylake design that came out 20 years later in 2015, What really happened in those 2 decades was that all of the buffering structures became larger, all of the caches became larger, all of the issue queues, the reservation stations became larger. The machine itself became a little bit wider. It went from sort of a 3-wide machine to about up to a 5-wide machine. And there were a few additional execution units added, but really that's it. It was pretty incremental, pretty much just, let's make this structure a little bigger because we can gain 0.5% here, or we can gain 0.5% there. But fundamentally, we've been building sort of the same microarchitecture, for 25 years now. Not a whole lot has changed there, which is a pretty depressing situation to be in. And in fact, if we think about this from the perspective of the design cycle, that has also changed. So kind of revising the Pentium Pro's design life cycle, we can revise it to match what happens today. So we conceive of a new CPU design. For the microarchitecture, we largely just copy and tweak what we already had. The performance model is already pre-existing. We pretty much just copy that and tweak that a little bit. And then the behavioral and structural models also exist, or even if we don't have our own designs, we can probably just go out and buy one. We can license one off the shelf and maybe tweak it a little bit and get that done. And then this whole bottom right quadrant here kind of goes away, right? We don't do logic design or circuit design or layout anymore when we design CPUs. Instead, we rely on standard cell libraries from whoever the process vendor is, TSMC or Samsung. We use off-the-shelf physical design tools and timing tools to facilitate going from a register transfer level design to an actual chip. And of course, once the chip tapes out, we still have to do silicon debug. But the main thing here is that there's not much new going on in the top half of this graph, and there's virtually nothing new going on in the bottom half of this graph. So a lot of the opportunity for innovation that we used to have as computer architects has been sort of ruled out, right? There just isn't much we can do because we're stuck in this design flow that limits what's possible. And what does this really mean? What it means is we've sort of boxed ourselves in as designers with a whole bunch of limitations. Our microarchitecture will stagnate because we're sort of effectively stuck in this local minima that is really just kind of a minor evolution, from a 1995 microarchitecture. We can't innovate on logic because that's all outsourced. That's done by, the standard cell vendor. We can't innovate on circuits because, again, that's outsourced. We can't do any co-optimization of devices or circuits or logic because our design flow really doesn't allow that, right? All of those things are fixed, and all we can really do is map our RTL to the existing elements in our standard cell library. And then finally, any attempts to do innovative things in terms of storage elements like latches or flip-flops, or even our clocking strategy, again, very little opportunity for that. We have to use standardized design tools to design our clock trees. We have to use standardized timing closure tools to make sure that everything works correctly and doesn't have any timing glitches and so on. And so we're kind of stuck in a mode where we really don't have a lot of opportunity to innovate. And as a result, we kind of end up making these designs that, maybe follow the mantra, shrink it, tweak it, ship it, right? That's what we're going to do. We're going to take our previous design, shrink it to the new process, tweak it a little bit, and ship it. Because there are many, many impediments that stand in the way of trying to do more innovative things. The advantage of doing this, of course, is that it is fast and easy, and we can ship a new smartphone SoC every 6 to 12 months because a lot of the steps in the process have been really streamlined. But I think the result is kind of predictable. There's not a whole lot of opportunity to innovate. There's not a whole lot of new things going on in this space. And so my intent in this talk is to encourage you as designers of future systems to try to question some of the assumptions and question the wisdom of being stuck in this state as much as possible, and so that in future designs we'll hopefully return to a little bit more innovative approaches to all of these problems. All right, so next I'd like to go over a few of the experiences from my career that I think hopefully will illustrate my point. And so the first topic I want to spend a little bit of time on is something called the Dataflow Limit. So, so we saw this table earlier. This illustrates various studies that have been done over the decades trying to understand how much instructional level parallelism exists. So what is the limit at which we can execute these programs if we try to extract as much parallelism as is there in the programs themselves? And as we already discussed, these estimates varied wildly, but one of the things that I would like to encourage you to do as a researcher thinking ahead is to identify words like limit that purport to claim that there's a fundamental boundary here that we cannot get past. This is one of the things that I was fortunate to do as part of my PhD research. I addressed this particular question of, is the data flow limit really actually a limit? Turns out the answer is no. We can actually get past the data flow limit if we employ various microarchitectural techniques to do so. And so on the left here, we have an example of a simple data flow graph with 4 instructions, which can execute in 3 cycles if you adhere to the ordering relationships specified by the dependencies between A and C, B and C, and C and D. So the data flow limit for this snippet would be basically 1.3. But it turns out that if you predict the outcomes of these instructions, so if I actually predict the values that A and B will generate, and similarly what C will generate, then I can actually execute these 4 instructions all concurrently, all in parallel, and the limit in this case will be 4 rather than 1.3, or the available instruction level parallelism, assuming these predictions are correct. So I have to make these predictions, I have to feed them to the dependent instructions C and D in this case, and then when I do execute A, B, and C, I have to verify that the result that I got actually matches the prediction that I made. But as long as my predictions are correct, I can actually improve the performance of these kinds of programs beyond what was traditionally viewed as the data flow limit. So there was considerable academic interest. Dozens of research groups participated in follow-on work. Hundreds of papers were published, all kinds of proposals. And there was some effort to try to get this into a real CPU. I went back to IBM after my PhD and tried to get this into a PowerPC part. There was a group at HAL, which was building Spark-compatible CPUs. They worked on this. And then Chris went back to Intel and tried to get this into an Intel part. And none of those efforts bore any fruit. And I think partly because the performance benefit was pretty modest. The power consumption for this approach was pretty high. It introduced actually a lot of complexity and potential correctness issues, hence risk. And it really, for these reasons and for the fact that simply, shrinking, tweaking, and shipping was still a more appealing path, it sort of died on the vine. There has been some recent design team interest, and there's been some academic recognition of the significance of this work. So hopefully it will come back to life in the near future. We'll see. All right, but again, just recapping, noticing that the word limit was being bandied about kind of tweaked my interest and tweaked our interest as a research group to try to see if in fact this was really a limit or this was something that we could actually exceed. All right, so the next example I want to talk about a little bit is from my experience working at IBM in industry, trying to translate a research effort to an actual product. So in the late 1990s, there was an industry race to building, greater than 1 gigahertz CPUs. So Digital Equipment Corporation was working on a follow-on to the Alpha 21264. Intel was working on a follow-on to the Pentium Pro that would hit this kind of frequency target. And IBM had an internal project that was, staffed at the time that I was there to build an Alpha 21264 like aggressive, out of order, but greater than 1 gigahertz CPU. At the same time, a group at IBM Research, it's a small group of less than 10 people, had designed a prototype that used an exotic dynamic logic family and was a full custom design, every transistor laid out by hand. They had designed a prototype that was a single issue, 4-stage pipeline with a single cycle cache kind of CPU that they published. So this is the JSSC paper that described it. Here's a die photo of it. And this was a research prototype that my group at the IBM server group, so my team was kind of tasked to try to make an attempt to productize this. Could we build an actual CPU out of this that was industrial strength and that would compete in the server marketplace? So what we proposed at the time was an in-order 2 wide 2 to 4 threads per core, and then 4 to 16 cores per die in quick succession with some die shrinks and some process technology improvements coming out. So this is what we proposed. It would have been, again, well above a gigahertz right off the bat, and improving from there. It was achievable because of some very restrictive design rules that we had put in, or that the design team had put in. I was really just involved on the performance evaluation side of this, and a bunch of cross-layer optimizations to, again, basically build a very shallow pipeline, but still at a very high frequency. So very, very kind of unusual design point, given that everyone else was building very deep pipelines, very large out-of-order machines to get to this high-frequency data point. We were saying, no, you can get there with a narrow in-order machine with a very shallow pipeline. We also, were purporting to do this with a smaller, 10x smaller design team than the current plan of record. And I think that really is ultimately what ended up, killing this proposal. Was we were essentially going up against the executives who had decided to commit to a 400 engineer design team for the Power 4. Hey, we can now build a follow-on part that's going to be better in every way with 40 engineers. Would you please fund us? Without really realizing that made them look pretty foolish in front of their bosses to say, well, 2 years ago we decided we needed 400 engineers. Now we think we can get by with just 40. That would call into question their judgment from the previous decision. So I think ultimately it's that kind of political process that ended up squashing this design. But it is pretty interesting that 3 years later, the Afara Web Systems startup came out of Kunle Lokutun's group at Stanford. Sequoia funded it with millions of dollars to build a part that looked very much like this, like the one we were proposing in 1998, and that came to, eventually evolved into, was acquired by Sun and became the sort of mainstay Spark processor for more than a decade of that product line's lifetime. So, yeah, so, you have good ideas. They're counter to what everyone else is doing, and sometimes they, don't come to fruition. But again, I want to encourage everyone to stay on that track, to think about contrarian ways of approaching these problems, contrarian approaches that will perhaps lead to a much more interesting space for all of us to occupy as computer architects. All right, so next I want to talk about some of the impacts of the end of so-called Dennard scaling. So scaling is something that comes up in every keynote. So I'm just going to throw up my Moore's Law slide quickly here. And the only thing I'll say about this is I want to quote my former colleague Mark Hill from Wisconsin, who answered the question of when will Moore's Law end with the answer, my answer is never. That way I will only be wrong once. So I think that's a good strategy. I think we're continuing to see scaling gains. Maybe not quite at the same rate as we've seen in the past, but I think there's just too much money invested and too much opportunity there for us for scaling to stop anytime soon. A variant of Moore's Law was Dennard Scaling law that he described in 1974. And I'm not going to get into all the details, but the main idea here is that if you scale by a factor lambda in every process generation, then all of these attributes of the design, like the device dimensions, doping, voltage, current, capacitance, delay, and power, all scale inversely with that scaling factor. And the end result is that you end up with a power density that doesn't vary with the scaling, which means we have constant power density, which essentially means we get double the devices for free as long as this Dennard scaling rule holds. And so as long as we had Dennard scaling, everything was great. There were no trade-offs at all. We doubled density every 2 years. We got improvements in switching speed. We got reductions in supply and threshold voltages. Unfortunately, this didn't continue forever. This ended starting around the year 2000. And so we're continuing to get device scaling and some frequency improvements. But fundamentally, our designs are now power limited because our power density, if we naively just double the number of devices in the same area, our power density also increases. And we end up melting our chips if we do that, or blowing our power budgets. And so power has now become the primary design constraint. And this is sort of since around the mid-2000s has been a big driver for the work that we've been doing in my research group as well. So I'm going to talk a little bit about a specific project that we've done in that space. And that project was really motivated by some data that came out of NVIDIA, as they were working on an SoC that included a Cortex A15 out of order CPU in it, that kind of broke down the power consumption based on the different components within the design. And if you just look at this one pie slice here, integer execution and data cache, you can kind of view this pie slice as the useful work being done. And you can view all of the other pie slices in this diagram as overhead, just because we want to keep the execution units and the load store ports in our machine as busy as possible. So we want to do all this other stuff to feed the execution units. And there's similar data that came from Intel that's a little bit less pessimistic. You know, if you sort of attribute half of the cache power and all of the integer execution power to useful work, then you know you're a little more than this pie slice, but still a big chunk of the remainder is sort of wasted in some sense on overhead related to making sure that we have useful things for the rest of the CPU to do. And so, is this really the way we want to live? Is this the kind of designs that we want when we're facing facing an era of design where we're fundamentally power limited? Do we want to spend this much power on things that really aren't contributing to the program's execution? They're just contributing really to making sure that the execution units are busy. So that's the sort of fundamental question that we started to ask, right? That has there been a design objective inversion from the historical perspective of hardware being expensive, right? We wanted to optimize every gate, every wire, every cable, every unit. We wanted to maximize the utilization. Hence, we wanted to, have this mindset of minimizing, those units and minimizing the cost and maximizing the utilization. But has that kind of been turned around its head now? Now power is the limiter. Power is expensive. Devices and wires on chip are inexpensive and getting less expensive with every process generation. So maybe we should minimize the capacitive load and minimize the activity of those devices and wires, but worry a lot less about their area cost. And so that's really the question that we've been struggling with. And if that's indeed the case, then we should really be designing logic that is simple, infrequently used on both the sequential and combinational side, and maybe isn't so concerned about the area cost and the utilization. And so we've been advocating for something that for buzzword purposes we call lazy logic as an approach for designing future systems. And so to demonstrate the value of this approach to designing CPUs, we really needed to revamp the whole core microarchitecture. We basically had to make some comprehensive changes to how things were done. And then we wanted to show that, hey, if we do this, we can actually build a competitive design, something that has matching performance to a high-end out of order in terms of IPC or ILP or per clock performance, but that also has dramatically reduced energy per instruction in all of the affected structures. And so this is the work that we did that culminated in a paper that came out at ISCA 10 years ago called CRIB. And I'll talk a little bit more about what that design looks like. So that design, again, is predicated on this idea that we're no longer living in a device-poor era, right? We don't need to drive utilization as high as possible. We don't have to maximize the performance return for each device. We don't have to have this policy of kind of a king ALU, right? The ALU sits there like the king, and basically the royal court is responsible for making sure that whoever needs the king's time comes in, presents their case, resolves the case, they get moved out, and the next pleader before the king comes in as quickly as possible. Where the ALU is sort of the critical resource, and we want to make sure there's always something for that ALU to do. This kind of policy or design approach translates into deeply pipelined execution lanes, so we get something there every clock cycle. We need large multi-ported register files to make sure we can get operands to that ALU, and we need very complex control logic in terms of renaming storage resources and scheduling all of these operations at just the right time, that are all very not only difficult to build but difficult to scale to larger sizes of windows, and also introduce power, thermal, and scalability problems. So rather than building machines in this way, maybe we should build machines that have more of a pauper ALU approach, where we have ALUs sitting there begging for work to do, right? Give me something to do because I'm just sitting here idle. So let's provision as many ALUs as we can afford in kind of a spatial structure, Let's place instructions into these execution stations. Let's distribute our register file across this sea of arithmetic logic units. Let's route operands to these arithmetic logic units. And then let's implement localized control, data flow, and dependence resolution mechanisms that are easy to design, are easy to scale to larger designs, and don't introduce any critical path delay problems and so on. And also, by the way, consume a lot less energy. And so this is what we did. We designed such a system, and we found that not only was it effective at reducing power, it was also useful as an enabler. So it enabled us to do a bunch of things that previously were either difficult to do or impossible to do. So we eliminated pipelined execution lanes. We completely got rid of multi-ported register files. There isn't anything that looks like a register file anywhere in this design. We don't need register renaming in the classical sense. We don't need any scheduling logic that does wake up or select. We have very, very few clock loads anywhere because we have very few clocked elements in the design overall. But not only that, we can enable things like efficient speculation recovery. So when a branch is mispredicted, it's very easy to clean up and restart execution at the branch target or the branch fall through. We can also do things like support variable execution latency. So if a cache access takes 3 cycles, 4 cycles, 5 cycles, 6 cycles, depending on which part of the cache you're actually fetching data from, that fits very naturally and easily into this localized control mechanism, whereas it fits very poorly into traditional classical out-of-order designs, which have to schedule things so far in advance that they have to assume that every operation has a predetermined fixed latency. Unfortunately, I don't have time here to go into the details of exactly how crib works and how it's designed, but to make the long story short, what happens is because we're placing the ALUs in the spatial organization and we're just connecting them to each other directly with muxes, we get rid of a lot of the structures that you see in a conventional design that consume area and energy. So this slide just summarizes that result. So this is all based on standard cell synthesis to a 40 nanometer process of a 2011 era high-end Core i7 CPU, the Nehalem microarchitecture, compared to crib. So on the left here, you see that the rename table, the reorder buffer, the reservation stations, and the register file consume the lion's share of all of the energy in the back end of this processor, energy per instruction. On the right-hand side, you see that all of those pieces are eliminated in the crib design, and those add up to 81% of the total energy budget of that Core i7. And all that's left is really the level 1 data cache DL1, the load store queue, and the ALU. Both the data cache and the load store queue are actually consuming a lot less power in the crib design because we can utilize design approaches that are incompatible with conventional out-of-order pipelines, such as variable latency caches, using line buffers, such as interleaved and banked load store queue structures that cause deadlock problems in conventional designs. And so those pieces of the pie actually shrink. The ALU piece of the pie here actually grows a little bit, and the reason it's growing a little bit is because we're actually including all of the muxing that is included in the interconnect in the spatial microarchitecture that routes operands around. We don't have an easy way of separating that out, and so it's the ALU plus the interconnect as opposed to just the ALU on the Core i7 side. So the bottom line is most of the power hungry structures are completely eliminated, and we are basically eliminating about 80% of all of the energy and power in the back end at comparable performance levels. Okay, so summarizing this portion of my talk, as presented in the ISCA 2011 paper, as well as Erica Gennadi's thesis, and there was a lot of follow-on work done in Mitch Henge's thesis and Vignan Kathinti-Naresh's thesis as well, and related publications. We basically showed that we can match the performance of a high-end CPU, but we can knock out 80% of the back-end power that is really there to, again, enable out-of-order execution in a conventional ALU, limited number of ALU type of data path organization. This design is also a great fit for lots of other optimizations, and these are the kinds of things that Mitch and Vignan looked at: back-end loop caches, exploiting control independence, etc. Again, I unfortunately don't have time to get into those, but there's a lot of interesting work there as well. There have been some efforts to try to push this into a commercial product. We're running into the same kinds of complaints and problems that we, seem to run into a lot of the time where, oh, our design flow doesn't support latches. You require latches in your design. Well, we actually have a way to get around that. How do we get to timing closure? You have multi-cycle delay paths here. Our tools don't support multi-cycle paths. Every latch to latch or flip-flop to flip-flop path has to be a single cycle. Otherwise, our timing closure just doesn't work. Well, yeah, these are challenges. You don't get an 80% reduction in your energy per instruction in the back end for free. You have to be willing to make investments in and take risks in timing closure as well as your overall design flow. And there are other issues where some mux span issues have been raised as a concern, but I don't think those are as critical. All right. Moving on to my next example of sort of trying to think a little bit differently and questioning things, I'm going to talk a little bit about multi-cycle paths. So I mentioned that the crib design has these multi-cycle paths where multiple instructions are kind of daisy-chained behind each other, and the computation proceeds through those ALUs that are connected back-to-back in more than one cycle, depending on the height of the data flow graph. So given that this was already the case in this design that we've been working on, we started thinking carefully about, is there anything we can do with the fact that when you have a multi-cycle path, you're actually accumulating potentially a whole bunch of cycle time slack. So a lot of people have worked on timing speculation or even asynchronous designs that try to take advantage of the fact that in our latch to latch path, we typically have a worst case combinational flip-flop delay, worst case combinational delay, some setup time for the downstream flip-flop, and then some guard band. Can we take advantage of this guard band? Can we eat into this guard band? And can we perhaps take advantage of the fact that the combinational delay is set up to be the worst case combinational delay, and we can potentially eat into that as well. And we started thinking about the fact that, well, in a multi-cycle path situation, we have a lot more opportunity because we now have n instructions or n combinational delays that are being accumulated, and we're amortizing all of these other terms, the guard band, the setup, and the flip-flop delay across effectively multiple cycles of work now. So we have potentially a lot of slack that's accumulating here. Are there some interesting things we can do with that? And it turns out that we think there are. So we, at a very high level again, and this is PhD work from Gokul Ravi, and we did some collaborations with Tushar Krishna from Georgia Tech as well on this. But the idea is separate the functional blocks in your pipeline with latches, just like you would in a normal design, but control the latch clock so that dependent operations are actually there concurrently, and the computation can proceed from one block to the next in an asynchronous way. And then build a simple little counter circuit that sits next to it that understands the behavior of these instructions with respect to how much slack they may or may not have. And this simple adder-based logic just accumulates the delay on the fly and then keeps track of it. And once the accumulated delay reaches an entire cycle, then you basically steal a cycle. You sort of clock things in one cycle early. And so you end up operating in a more or less synchronous fashion. Everything is still happening synchronously on the existing clock boundaries in your baseline design, but every once in a while you get to steal a cycle. And it turns out every once in a while is actually pretty frequent. And you can get significant performance benefits from this for, sort of the original crib style data path with lots of ALUs in it. So we published some work on that. We actually adapted it to an out-of-order core. This appeared at HPCA in 2019. And then we've also been doing some work adapting it to network on chip kinds of applications, where now we have packets flying through the network on chip in a more or less asynchronous fashion by taking advantage of this slack accumulation mechanism that we've proposed. All right, so again, the idea here is to sort of question the conventional synchronous way of doing things and say, hey, maybe there are things that we can do here that are going to now make life a little bit more difficult in terms of correctness and in terms of timing closure and so on. But if there's significant opportunity, maybe it's worth pursuing. And as you might expect, the shrink it, tweak it, ship it crowd says, no, we can't do this. We don't understand latches. We don't know how to do timing closure, etc. We give up. We just want to keep iterating and getting our incremental gain generation after generation. All right, the final quick section I want to talk here goes up a little bit in terms of abstraction layers. So I want to talk a little bit about making assumptions about the kinds of data types that we expect to do computation on and trying to do something a little different here. And so I'm going to motivate this by talking a little bit about some of the evolution that we've been seeing on the floating point representation side. So for many decades, all we've really been using are sort of either single or double precision IEEE standardized floating point representations with a sign bit, an exponent, and a mantissa. This has been, evolving recently. So bfloat 16 is a 16-bit version of this that is now been standardized. As a competitor to FP16, we have bfloat 16, which looks similar to single precision, except that it just has a lot fewer mantissa bits, so a lot less precision, but has the same range as we have with a single precision float. So it has some advantages from a numerical analysis standpoint in that way. And then also there's been a proposal to do shared exponents, which is not a new idea, but been recently brought back into the field by the Nirvana startup that Intel acquired. So that's on the floating point side. A lot of this has been driven by the need for having efficient representations for parameters when you're doing DNA training. There's been also an evolution on the fixed point side, which historically was kind of going from narrower to wider because wider was considered better, more precision, larger address range, etc. But that's again been kind of inverted lately, where people have been pushing back towards narrower representations, primarily because storage, interconnect, data path, and compute logic all become simpler, cheaper, lower energy, and that again is now being driven by deep neural network inference rather than training so much. So the question that springs to my mind when I see this kind of thing happening is, how narrow can you go, right? What is the limit here? Can we do something? Can we do something even more extreme than these handful of bit types of representations that people are now actually using and deploying in things like edge IoT inference engines? The least information that we can convey or process in a digital system is 1 bit. And in fact, if we have 1 bit, we can increase the amount of information that we convey by streaming a bunch of bits in a row. So we call this a bit stream. Other names for it are stochastic computing. But this is actually something that arose because we've been doing a bunch of work on biological spiking networks in our group. And it turns out that neurons actually use something called rate coding, which looks an awful lot like a stream of bits, except it's a stream of spikes that the neurons are generating. But information is posited to be contained in the rate at which those spikes are occurring. And so that's sort of illustrated here in this diagram, where the quantity or the value that's being represented is captured by the frequency of the spikes as you go from left to right in a neuron firing chart like this one. So, and then finally, stochastic computing, is an approach that was proposed by von Neumann originally, and then in digital form by Gaines in the late 60s, where the idea was that we would represent numbers, like in this case fractional values like 4/8 or 1/2, 6/8 or 0.75, coming in as inputs S1 and S2 on the left here. We could actually implement multiplication with a simple AND gate by simply ANDing each of those bits in time, and then considering the stream of bits coming out the other side is now the answer. And you see that you get an answer that is pretty close to the correct answer. And in fact, over time, the more bits you stream through here, as long as they're properly randomized, you converge on an answer that's very closely matches the expectation. So this is an approach that maps itself nicely if your underlying data is already represented in this bit stream format. So this got us interested in thinking about ways to do this. And again, the reasons why are pretty obvious. It's a very flexible representation. The data paths, like a multiplier, is just a single AND gate, so they're very low cost. And again, it's the preferred representation for sensors and even actuators in many embedded contexts. It obviously has some disadvantages as well. It's a very inefficient representation, again, because for precision, it's linear in cost versus logarithmic, like a binary encoding would be. The computation, if the bit streams are long for the required precision, can be very inefficient. And there are lots of algorithmic issues, right? We don't have a full set of operators, so we have to invent new ones or live without them. Pipelining and streaming computations are difficult because sometimes you have to serialize to figure out what the value is before you can pass it to a downstream operation. A lot of analytical tools like Z-domain analysis from signal processing just don't work. And we've published some work on things like range and precision and scaling. These are tricky problems to solve. We have some potential solutions for them in a Frontiers paper that came out a couple of years ago. And finally, there's a lot of practical issues. There are no software tools, there are no languages, no compilers, or there were no software tools or languages or compilers. And then also, you have to ask yourself, well, this sounds like fun, but are there really any compelling use cases out there that we want to look at? All right, so we've attacked the development tools problem. So a lot of this work has been done by my PhD student, Kyle Darawala. So he has implemented 2 generations now of a tool called BitSad, which is essentially a compiler and automated hardware synthesis environment that allows you to specify using a high-level language programs that will then operate in this bitstream domain. And it's written in Julia, so it's a familiar language to people who are working on machine learning kinds of applications already. And it has lots of syntactic sugar that makes life easy. And again, it automatically then spits out hardware that you can synthesize for deployment either on an FPGA or potentially even an ASIC. And this is open sourced and available from this link. So I encourage you to take a look if you're curious. We've also thought hard about applications, and I'll just mention 2 here. So my PhD student, Suresh Koram, has been working on Bayesian neural networks or Bayesian inference. Now, the basic idea with Bayesian neural networks is that you want to be able to measure the uncertainty of the results that come out of your neural network. So if you have a classifier that tells you you're looking at a cat, you'd like to know, well, are you 90% certain that it's a cat or 60% certain? Because in many contexts, that's actually a very useful piece of information to have. So Bayesian neural networks basically are able to do this because they're trained to learn not just a set of parameter values like in the convolutional layers or the fully connected layers, but actually distributions for these parameters. And then when you exercise these during inference, you actually sample from those distributions and then take multiple samples through the network, and you can then estimate the confidence of your result based on those samples. And so the simple toy example of this is this very simple classification task where the blue dots and the red dots have different labels, and you can kind of see from the intensity of the background color that the Bayesian neural network is telling you that the further you are from the decision boundary, the more confident you are. The closer you are, the less confident you are. And we're able to demonstrate this for CPUs, but also our BitSat implementation achieves a very, very similar and compelling result. And stochastic bit streams, the argument we're making here, are a natural fit because they're already stochastic in nature. So what you really want to do is use stochastic hardware to implement stochastic algorithms. This is just another result from an audio hot word classification task that shows that as we increase the SNR of the samples that we're trying to classify, the accuracy goes up, shown on the right-hand side, but the uncertainty also goes down. And so the uncertainty measurement from the Bayesian neural network implemented in this bitstream computing context does exactly what you want it to do. You want it to have better confidence for signals that we already know have better SNR ratios. So that brings me to the end of my talk. Thank you for your attention. I hope I've been able to convince you that perhaps due to the end of scaling, but also due to other causes like the design flows and the foundry model that we use today to build computers, computer design is stagnating. And I think to break ourselves out of that mold, we really need to come back and question a lot of the assumptions that go into the design decisions that we make as computer designers. Hopefully the examples from my career were illustrative of that and would inspire those of you in the audience to really try something different the next time you're tasked with designing a new computer. And really what I would like to see our industry do is move from sort of computer design as an exercise in conservative risk management to back to something that looks a little bit more innovative and interesting and exciting. I do want to quickly acknowledge the work of others. Tushar Krishna helped us with the NOC work. Chris Wilkerson and John Shen worked with me on value prediction. The CRIB project has been a long-running one with Erica Gennady, Mitch Henge, and Vignan Kathinti-Naresh as PhD students that were heavily involved in that. The multi-cycle Slack work was Gokul Ravi's PhD work, and the bitstream data type stuff that I talked about near the end is really the work of Kyle Darawala, Sarush Koram, Hengzhou, and Carly Schultz, who are currently in my lab. We've been fortunate to be funded by the National Science Foundation, the Air Force Research Lab in Rome, New York, as well as Qualcomm Oracle and Google Research. At this point, I'm happy to take questions.